The point of this lab is to use Newton's second law and the energy principle to predict and understand the motion of a mass that is swinging in an arc while oscillating on a spring. I first analyzed the motion of the mass using tracker. I then applied fundamental physics principles to model the predicted motion using VPython. I compared the predicted and observed motion of the system and discussed the energy changes. My computational model predicted the motion accurately. However, there were minor discrepancies. We first start off with Newton's second law, which states that the final velocity is equal to initial velocity plus F net divided by mass times delta t. F net in our system is the force of gravity and spring force. We are assuming that air resistance is negligible, and these two are the only two forces. The energy principle states that the change in total energy is equal to work done by the surroundings. There is no energy transferred to or from the surroundings, so the change in energy in our system is equal to 0. Delta E is equal to the change in kinetic energy of the mass plus the potential gravitational energy plus the change in spring potential energy. Here is the video of the spring and tracker. I extracted X and Y position data to use in initializing my model. The initial position is negative 0.115, negative 0.632, 0 meters. And the initial velocity is 0 meters per second because the mass started at rest. In order to find the spring stiffness constant, Ks, I used the equation for oscillation period t. Using Y data, I found t to be 1.52 seconds and Ks to be 6.87 newtons per meters. I also need to find the relaxed length of the spring. When the spring is at rest, F grav and F spring equal to each other. I rearranged the equations to solve for the relaxed length of the spring, which was 0.126 meters. Now I can make my model. Here's where I inserted the initial conditions and other constants. L is the length of the spring, L hat is its unit vector, and S is the magnitude of L minus L naught. The forces acting on the system are F grav and F spring. Their equations are inserted here, and F net is equal to the sum of F grav and F spring. Here is Newton's second law that calculates the new velocity of the mass, which is used to update the position of the mass. Here is a graph of the predicted and observed positions. In the x direction, there are a few discrepancies. This could be due to air resistance, which was not accounted for when calculating the net force. In the y direction, the predicted position almost perfectly fits the observed position. The discrepancies at the crest and trough could be due to human error in using tracker as well. In order to calculate energy changes, I needed to define the equations for the kinetic, gravitational potential, and spring potential energies. I inserted those equations here. In this while loop, K initial is equal to K, UG initial is equal to UG, and US initial is equal to US. To calculate the energy changes, I inserted the equations for delta K, delta U sub G, and delta U sub S here. Here are the graphs of the energy changes. Delta E, the yellow graph, is equal to 0. The green graph, delta UG, the red graph, delta US, and the blue graph, delta K, look like they add up to 0. As you can see here, the green and red graph almost cancel each other out. But when the blue graph is added, their sum becomes 0. So to answer the what does it mean question, yes, the energy principle is satisfied because the change in the total system energy is equal to the sum of the individual energy changes within the system. Comparing the periods calculated using X and Y position data, we find that the periods are not the same, which contributes to the complex motion of the system. The periods are different because the mass travels further in the X direction than the Y, making the time it takes to make one oscillation longer. Also, the oscillation period in the Y direction pretty much stays constant, while the period in the X direction changes, as you can see here. In conclusion, fundamental physics principles like Newton's second law and the energy principle can be used to predict the motion of a system, however complex.